This is problem number 8 on the sample test problems for test number 2. The graph below shows a function f, which expresses Newton's distance from the starting line in miles as a function of the number of hours x, which he raced. A, find an exponential function that goes through the first and last points of the graph above. So let's go ahead and grab the coordinates of the first and last points. This is 0, 1. This is 10, 5. And we'll go ahead and start with the exponential, like the basic exponential function. So something like P0 times a to the x. You can use different letters there, but you need to make sure your variable is up in the exponent. Okay, there's a little bit of a gift given to us in this case. The y-intercept is P0. So in our case, P0 is 1. So that means that y is equal to 1 times a to the x, or simply y is equal to a to the x for this exponential function. Now we need to make this function hit the last point. So instead of y, we're going to put 5. And instead of x, we're going to put 10. And the goal is to solve for a. Now to solve for a, it might be tempting to use logs. That's how you would solve for a variable up in the exponent. But here the variable is just the base. So what we want to do is raise both sides to the right power. The right power is the 1/10. Equivalently, it means take the 10th root of both sides. So what that means is that 5 to the 1/10 is equal to a by taking both sides and raising it to the 1/10 power. Or like we said, we could have thought of it as a 10th root of both sides. Technically, I think when we take a 10th root, we should put a plus or minus in, but a is always a positive number, so I think we're fine ignoring the minus part. So we've got our formula. Exact formula is going to be just y equals the 10th root of 5 raised to the x power. But we can type this in and get a decimal, so let's try that now. So we want the 10th root of 5. A couple of ways to do this. One way is to type the 10 for the root, go into math. Right here, number 5 gives you a general root, so we hit 5. And then the 10 is the 10th root, and the number that goes in here also happens to be 5. So this should give us our decimal. Or if you prefer, you can just type in 5 raised to the 1/10. Don't forget parentheses there. And this should give us the same decimal. Or if you really want to be efficient, 5 to the 10 x inverse. You get to save one button press. So this is 1.1746. So that's our formula. And we'll move on to part B. According to your equation from A, when was Newton 3.5 miles from the start? Solve this algebraically using logarithms. Okay, first let's just look at the graph and try to get a sense of reality. So 3.5 miles from the start, that is on the y-axis, the horizontal axis. So somewhere about there. If we go over to the curve, so there's your 3.5, and then go straight down, we should get some number around 7.5. So when we do our algebra, better get something close to 7.5. All right, so let's take our equation here, and we want to make it equal to 3.5 miles that's given in the problem. So we have 3.5 is equal to 1.1746 to the x. And when you're trying to solve an equation and the variable is in the exponent, we use logs. So let's take log of both sides. We'll take the natural log of both sides. You could use log of any base, but base e is the base of choice in calculus. So ln of both sides. And then this really nice property of logs says you can take log of a number to a power, and you can bring that power right in the front. And so we're going to write that over here. ln of 3.5 equals x times ln of 1.1746. And then finally, to solve for x, divide both sides by ln of 1.1746. So we'll type this onto the calculator, again hoping to get something near the 7.5 that we just saw from the graph. Okay, so we're doing ln of 3.5 divide by ln of, and then instead of retyping that, which is rounded, we'll just do second answer. This will be the most accurate answer the calculator can give us. Let's just see how different the rounding would have been. Probably not too bad in this case because we wrote down 4 decimal places here. So ln 3.5 divided by ln 1.1746. So you can see the answers agree to the first 2 places here, and then we're off by about 1,000th. But whenever you can, use the number that the calculator has stored. So 7.784. And that is reasonably close to the 7.5 that we estimated from the graph in green. So how come it's not perfect? Well, because this graph is not necessarily the graph of an exponential function. So all we did is find the exponential function that hits the first and last points, but it might miss the rest of the graph by a little bit or a lot. In this case, it didn't look like it missed it by too much, but it turned out that for our example, we would have had to get out here to about 7.8, which means that the real curve at 3.5, the exponential one that we found anyway, would have been out here. So maybe the exponential function that we found is a little bit less and then comes up and hits, just to give us a sense of why it wasn't perfect. Okay, so we'll get rid of all that and come down here to part C. Now assume the graph shows a quarter of a period of a sinusoidal function. Find its equation. All right, let's take a look at the picture again. So if this is the quarter of one period, then what does the rest of it look like? Well, it feels like if that's a quarter, then the next quarter is still on its way up, and eventually, maybe someplace up here, it reaches its peak, and that's half, and then it comes back down to do the second half. So I feel like if my choices are sine or cosine, and I know it says sinusoidal, but generally that means either sine or cosine. I feel like this graph right here, well, let's go ahead and remind ourselves of what sine and cosine normally look like. So here's y equals sine x, and here's y equals cosine x. And a distinguishing feature of the sine function normally is that it starts in the middle, whereas the cosine function starts up at the top. So where does this function start? Well, I would say it starts at the bottom. So there's no way to get the sine function to start at the bottom, but you could get a cosine to start at the bottom by putting a negative in the front of it. So that would make it start down here and then just reverse all the stuff that it did before. So I feel like most naturally for me, this is a negative cosine function. The answers can vary on this one, but I'm going to do negative cosine. All right, so let's see if we can't grab the important information from the graph. First, we're going to write down some general equation of a cosine function. So maybe something like this. A cosine b x minus h plus k. You can use any letters you want. I'll use these. And then each of the letters has to do with some part of the graph. So A is the amplitude. Let's see if we can figure out what the amplitude is. Amplitude is how far the thing is stretched from the middle. So if we're looking at a quarter of the graph, then the middle of this graph is here. And the question is, how far is it stretched from the middle? So it is stretched by that much. So whatever that distance is, that's the amplitude. So in our case, it's a 5, and it's a 1, and it's 4 apart. So the amplitude of this thing is 4. Okay, next thing we'll do is look at the h. H is the horizontal shift. And I think that by the way we've chosen to do this with a negative cosine, h is going to be pretty easy to find. We sort of naturally decided that we were going to let this be a negative cosine because it started at the bottom and was going up. just like it does, starts at the bottom and goes up. And so if we do that, then we don't need to shift horizontally at all. So by our choice, h is 0. Okay, next thing we'll talk about is k. K is the vertical shift, which is also known as the midline. So what is the midline for this graph? Well, it's the line that goes through the horizontal middle. I don't know if I said that right. Line goes through the vertical middle. Maybe that's better. Anyway, it's the purple line that I've drawn up here. It's called the midline. And in our case, it's up at 5. So this graph has been shifted vertically 5 because normally the middle of the cosine graph is at y equals 0, whereas up here, it's at y equals 5. So 5 is the value of k. And then finally, we need b. So b is very much related to the period. So let's first write down the period. So the period is how long it takes horizontally to do a complete cycle. So we're going to get that from the graph. So in this case, it takes 10 hours to do 1/4 of a complete cycle, or 1/4 of a complete oscillation. So if 10 hours is 1/4 of the whole thing, then how long is the whole thing? It's going to be 40 hours. So the period is equal to 40 hours. And then we just need to bring in another formula to get b. Turns out b is always equal to 2 pi divided by the period. 2 pi divided by 40, which reduces to pi over 20. So that's the value of b. So putting it all together, we get y equals, okay, a we said was 4, cosine of b we said is pi over 20, x minus h we said is 0, that was our choice, and then plus k at the end, k is positive 5. One important note is that we decided this was going to be a negative cosine. And even though technically the amplitude is always a positive number, we need to make sure we put a negative right there in the front. If we don't put that negative there, then it's not a cosine starting at the bottom, it's a cosine starting at the top, which means that you'd have to shift it horizontally to get the graph to land on the graph in the picture above. So here's our equation. We don't need to write that minus 0, so we'll just clean it up. Negative 4 cosine of pi over 20x plus 5. Part D, according to your equation from C, when, during the 10 hours shown, was Newton 3.5 miles from the start? Solve this algebraically using an inverse trig function. So again, we're looking to figure out when Newton is 3.5 miles away. And it's the same green dotted line that we're looking for. So again, our estimate should be about 7.5. So let's see if we can do some algebra and get some number near 7.5. Okay, so what we're looking for is to make this equation in the box equal to the 3.5 miles. So let's do that. 3.5 equals negative 4 cosine pi over 20x plus 5. Have to solve this for x, so we have a lot of things that need to go away, and we got to move them in the right order. So there's a negative 4 that needs to move. There's a cosine that needs to move. There's a pi over 20 that needs to move. And then finally, there's a 5 that needs to move. So we have to move them in the right order, trying to get cosine by itself. So the first thing that goes is the 5. So we'll subtract 5 from both sides. Next thing that needs to move is the negative 4. So we'll divide both sides by negative 4. Next thing that needs to move is the cosine. So we'll take the inverse cosine of both sides. I'll go ahead and cancel those two negatives. And when you take the inverse cosine on the right-hand side, it cancels with the cosine. So we're just left with pi over 20x. And then finally, to solve for x, divide both sides by pi over 20, or maybe a little better, multiply both sides by what number? 20 over pi. Okay, so let's type this in and see if we get anything near 7.5 that we get from looking at the graph. Okay, so 20 divided by second pi, inverse cosine is second cosine, 1.5 over 4. And one thing I'm going to do before I hit enter is think about the mode, because anytime I hit one of these trig buttons, I have to make sure I'm in the right mode. Right mode for this problem, because we chose to do this 2 pi over the period, right mode is radians. So make sure that your calculator is in radian mode. If you're in degrees, change it. You'll get a ridiculous answer if that's in degrees. There's nothing special about radians actually in terms of this problem. If we had done 360 over the period, we'd have a slightly different formula here. We'd make sure we were in degree mode and we'd get the same answer that we're about to get there. So that seems quite reasonable. We were expecting something near 7.5 from the graph, and this looks pretty good. So x is approximately 7.55.